Hello everyone and welcome to the 42nd lecture of the course Advanced Structural Analysis. We discussed the basic analysis approaches related to the matrix implementation. We introduced the general orientation for the space structures, and by identifying the rotation matrix, we are now in a position to solve the given problem for the space frames and the space trusses. As a simplistic example, we are taking in this course a space truss structure for which we will just show the calculations. The space frame structures can also be done in the similar manner, which can be utilized with the general rotation matrix which we defined in the previous session. Most of these computations are typically required to be done using the computer programs. So that is why manual calculations are not necessary or not feasible for these problems. We have already shared with you the computer program which is able to solve the general analysis for these space trusses, and we hope that it can be utilized for the similar problem statements. So this is a problem statement which we are starting with. We have given a space truss which appears in this manner, and now to consider whether to understand that, one must first visualize and understand that the structure is really appearing to them as a space truss. Space truss, as we said, that will have a members which are inclined not only in a within 2D plane, but which are also now oriented in a complete 3D space, which means that now if I look at the orientation of the system, so this is one of the joint which is over here, and from here a straight line connects to a member over here which is at the same level. So both are at the or I should rather say that both are at the position of the xz plane of the given system. But as far as the position of the y is concerned, the position for this given system is also y equal to 0, and this point is also at y equal to 0. But as I see that somewhere in the middle or the center of it, we bring one point which is a little bit away from the given system. Its coordinates are defined which are below the given axis y equal to 0, and that is where the members which are now connected, say from this initial point to this given point, the members which are connected, now these members no longer remain within one given plane or the specific plane of x of y, y of z, or x of z of the given system. So as the orientation of the members can take up the different planes of the given system, not necessarily a specific 2D plane of the given problem, this is called as a space truss, right. Now as a simple example or a simple cases where you can implement these problems, like simple industrial shed. If we typically look at the industrial shed, we can just consider that say one part of the member trusses have been identified, say something like this. In many of the cases we consider that the uniformity of the bay areas is existing, so that is why the one simple truss as a plane truss also can be analyzed. But in cases where say the uniformity does not exist, say along the length, the way the space truss is considered, there are some of the member spans which are say at a distance which are larger, then maybe there are some systems which are at a smaller or a further larger dimension of the system. So in those cases one is supposed to be, so in those cases if you consider now this as a part of the truss, so one need to analyze these systems with, so I think if you just make it in the same 3D manner, so all these members will be connected. So now if we want to analyze the given system with the non-uniform dimensions within these bay areas, one can also consider that the overall space truss can be modeled and can be analyzed in the given structural analysis program. Typically to make these programs or to run these kind of simulations in any standard software tool like StatPro, ETABS, one need to work out with all the member orientations and everything. But as a very simplistic tool, what one can do, one can easily generate say one particular bay of the given system by defining the coordinates of the point, keep on generating the respective new bays in the system by identifying the new coordinates of the system with respect to movement of only the another coordinate point, and easily provide this input to this to the given computer program and run this space truss for any given loading, right. So in fact we have multiple times done these kind of analysis for the realistic structural systems as well, and these analyses become much more faster compared to identifying the geometries in a standard software tool. So the utility of the course is not only limited to doing these problems manually, but the moment you are able to understand the computing analysis of the system, and you have the now understanding related to provision of the inputs in the given problem and any of the changes which are required based upon the given problem statements, you can easily do these computations using these provided computer programs as well. So as we said that in this problem we have the given members which are identified. The elastic modulus of the material, all the materials are of the same make, and they are defined with the elastic modulus of 80 GPa. L value is defined as 1 meter. So individually in the analysis, this dimension is defined as 3L, this is also 3L, this upper height is also 3L. So this way multiple dimensions are located with the value of L being 1 meter. The value of the load P, which is defined on number of positions like over here, is equal to 240 kilonewton. The area of cross section for member 1 to 3 is 0.01, whereas area of cross section for all the other remaining members is 0.02. So now before starting the problem, what we will do, we will label the members so that we understand that which are our member 1, 2, 3 in the given system. So this is the numbering system which we have adopted. The circled ones are the numbers of the members, whereas the direct numbers which are written, those are the numbers of the joints in the given problem. So we realize that the given system has total 6 number of joints in the given problem. So this is if I start with, this is the joint 1, this is joint 2, this is joint 3, this is joint 4, this is joint 5, and this is joint 6 of the given system. So we have total 6 joints in the given problem. Then individually when we look at the members, we have multiple members connected, starting with the member 1, member 2, 3, member 4, 5, 6, 7, 8 and 9. We have already discussed this part, that the choice of member numbering and the node numbering is to the user. User can label it as per their own wish, unless it is not defined beforehand. Like in this problem we already said that member 1 to 3 have different areas, so one need to know or one need to understand that which are those members 1 to 3 in the system, but otherwise this numbering can be done in any particular order of the given system. Now as input data, as a first step of the system, we go with all the nodes, define their x, y and z coordinates of the given system. So starting with say the node number 1, which is over here, we identify that the x coordinate which is in the given direction is equal to 2.5 into 2.5 plus 2.5, which means that total 5 units. L value is equal to 1 meter. Y direction, as it is in the y equal to 0 plane, so y value is 0, and z value as it is in the plus 3 direction along the positive z coordinate, so the value is 3 in the given system. So this way we are able to identify the individual coordinates for all of the points in the given system. I will suggest that you go through briefly all the points and see that the individual coordinate points which have been located for each of the member or each of the joint are clear to us. Like if I just go with the joint number 5, I understand that this is along the x axis at the x equal to 0, sorry, this is along the y axis in the system at x equal to 0. So the x coordinate is 0, y coordinate is at this height of the system which is 3L, so it is 3, and z, it is at z equal to 0, so it is 0, 3, 0. So I go to the point 5 and I see that it is 0, 3, 0 in the given system. Now as a next part, we also define that what are the restraints in the given system. For a truss member, we have the restraints only in the translation, so we define the restraint in the direction x, y and z, no rotations in the given system, no rotation restraints in the given problem. So in the case of the joint number 4 and joint number 5, joint number 6, we have all the translations fully restrained, whereas all the other nodes are completely free to move. So with this idea, we consider that joint 4, 5 and 6 have been provided with the values of 1, 1, 1 in the joint restraint vector, which means that if the member is restrained, we defined as 1, which means that yes, the member is restrained in the system. I think this we discussed in the previous part also, that how do we implement this idea in the code to extract the information of these individual node numbers to locate the sizes of the member stiffness in the rearranged form. This is one input part. Second, we need to go with the member input data. So we define all the members. So there are 9 members in the system. For each of the member, we define the 2 nodes, node J and node K in the system, and we also identify the member area and the elastic property of the given system. So this has been provided through Excel sheet. I think if you will see the code which we have shared with all of you, you will find that there are two Excel sheets which are also, there is one Excel sheet which is defined with it. One sheet inside that provides the node data, whereas the other sheet provides the member data of the given system. So once we are done with this member data of the given system, we are primarily done with the input parameters for the problem, except the loading parameters of the given system. We will come to the loading parameter in the subsequent steps. Now, as a next step, we need to identify the member stiffness. We have already said that to identify the member stiffness, first thing the user need to know the element local coordinate stiffness matrix, and that is a very simplistic one because it's a simple plain truss. If I identify this as the member I, which is having two of the nodes, say j and k in the given problem, I can locate that corresponding to these three translation directions only along the direction of the 1 and 4. I will be getting the contributions for the stiffness part, and that is what has been reflected in this relationship. For the local member coordinates in this expression, I am only going to get the contributions in the row number 1, 4 and the column number 1 and 4. The values have been identified with respect to the given problem. Now, once we have identified the stiffness matrix in the local coordinate, I also need the transformation matrix or the rotation matrix for the given system. So, rotation matrix for a general space structure has been defined by this formula. We are not again going back to the derivation that how did we arrive at this, but as a simplistic part, we did the rotation about the different axes and identified the fixed position of the member coordinates with respect to the generalized structural coordinates, and with their direction cosines we were able to identify the standard rotation matrix of the given system. Now, as a simplistic case, we also understand that for the given plane trusses, space trusses, we do not get the alpha which is the rotation about the member axis. We typically do not require it because as a second moment of area or the principal directions of the cross sections are not necessary. So, we can keep the rotation with respect to the direction x irrelevant, and that is where we introduce the cos alpha or the sin alpha with respect to alpha equal to 0 parameter, and that gives us the rotation matrix as C of x, C of y, C of z minus of Cx, Cy upon C of xz, C of xz, C of y, C of z upon C of xz, C of z upon C of xz with the negative sign 0 and C of x upon C of xz. So, with these values, I think the rotation matrix of the given system is known to us, and once the rotation matrix is known to us, we can easily evaluate the stiffness matrix of the given system, and that stiffness matrix, if I just write the expression, can be written as SMI, which is the stiffness matrix for any member I, and that is equal to the rotation matrix in the 6 cross 6 matrix arrangement with the transpose into SMI, which is the member stiffness in the local member coordinates, multiplied by the rotation matrix in the 6 cross 6 stiffness format. So, with this part, once we are able to identify the stiffness matrix for each individual member, we can start assembling them. So, as a simplistic process, if you will just cross check that the multiplication of this part with the rotation matrix, we will realize that in fact as the row number 2, row number 3, row number 5 and row number 6 are 0 for the given system, these expressions do not get introduced in the given problem. We get all the values only in terms of Cx, Cy and Cz of the given problem, and that is what typically is arranged here. It is taken from the given code only, where we evaluate the values of the C2, which is C into C, the cosine angles, sine angles and the normal angle of the given system, and with these parameters we evaluate the stiffness matrix of the given problem. So, this is the stiffness matrix in the global coordinates for the given member I. Once we are able to identify it, we can locate these values, like for the member 1, these are the stiffness matrices. Similarly, for any of the multiple members we can do. So, I have just shown here for member 1 and member 5 for the time being. What is now important, that once you locate for individual members, we should also extract the information that each member is contributing to which degrees of freedom in the given system. To understand it, for any of the member I, we have two of the joints j and k, and now probably we have done it multiple times. This degrees of freedom are 3j minus 2, 3j minus 1, 3j. These degrees of freedom are 3k minus 2, 3k minus 1 and 3k in the given system. So I will use these order of the degrees of freedom to consider that where the contribution of individual member stiffness is going, which means that when I look at the member 1, I see that member 1 is connected to the node 1 and 2. So node 1 or the node j is 1 and node k is 2 in the given problem, which means that with the node 1 I have the, if I say that the node 1 is there as a j value, I will have the 3 degrees of freedom in the system, which will be 1, 2 and 3 in the given system. Corresponding to k value equal to 2, I will have 3 degrees of freedom, which will be 4, 5 and 6 in the given system, which means that the contribution of the member 1 is going in the rows of 1 to 6 in the global stiffness, as well as in the columns of 1 to 6 in the global stiffness. While doing it, we should not remove the existing values, we will keep on adding the subsequent values in the given system. So this typically identifies, so as the S of S, the structural stiffness matrix of the global system, in the row numbers 1 to 6 and column number 1 to 6, we keep whatever existing values are there, and along with that we also add the contribution of the member 1 stiffness, right. I have written here directly as 1 to 6 and 1 to 6, but as you realize that these are defined with respect to the individual orders, I can call it as, say, some value a to a, and this value of a can be written as 3j minus 2, 3j minus 1, 3j, 3k minus 1, 2, 3k minus 1 and 3k. So I hope this makes now sense, because somewhere we have already discussed that how do we implement in the computing system. So this is the specific position of the overall stiffness matrix. I am going to the position of 1 to 6 rows and 1 to 6 column in the given system, or otherwise I can say that A, which are all the rows of the system which are labeled by these values, and A, all the columns of the system which are also again labeled by these values in the given system, right. So this is what we did for the given system. Now in the same manner, as a little bit different case, we can pick, say, the member number 5 also. So if I pick the member 5, I get the two joints, say the joint j which is 4 and the joint k which is 3. So I will now change the values over here. So this is 4 and this is 3 in the given system. So as we change the values of the joint j and k, we will get the different values of the stiffness contributions of the system also. So with respect to the value 4, we will get it as 3 into 4 minus 2, which means that it is 10, 11 and 12, whereas 3 into 3 minus 2, which means that it is 7, 8 and 9 in the given system, which means that if I pick the value of the stiffness matrix for member 5, it will be going to the position of 10, 11, 12, 7, 8 and 9 in the given system. So one should be careful in this case, because one should not go with the idea that 7, 8, 9 is to be appeared first, then you need to write 10, 11, 12. It is not this way. It is simply based upon the order of the node j and k of the given system. If the first node happens to be 4, which is scattering to the degrees of freedom 10, 11 and 12, then the first 3 stiffness contribution or the first 3 rows will go to the position of the degrees of freedom 10, 11 and 12. If the second node contributes to with respect to the node number 3, then the individual degrees of freedom with respect to that will go to the 7, 8 and 9 in the given system. So with this idea in mind, we are able to now assemble the overall stiffness matrix by individually calculating the stiffness matrix of the each member. So this is what we do. We individually define the stiffness matrix for each of the member, and finally we assemble the overall stiffness matrix of the given system. As we have got total 9 number of members in the given system, we have total 6 number of nodes in the given problem. So we get a stiffness matrix of the size 18 cross 18, because total 6 nodes means we have 6 into 3, total 18 degrees of freedom in the given system. And for each of the member, we are getting a 6 cross 6 stiffness contribution, and by doing this kind of a simple practice, we can identify where the individual contribution of each member is going in the overall problem. So this is what we have already done. Now once we are, so I'll just try to show maybe once, say for the member 5, as we show that this is 10 and 10, the first value. So this value should actually go to the position of 10th row and 10th column in the given system, that means over here. So this value which I just crossed should be 1.4186 into 10 to the power 5, right. So, this value I'll just put, say I'll just put x only, and I'll just say that this is the x which I am looking for. If I just say that some value over here, so this value of the given system, I call it as say y. So, this value should be located with respect to the row number 12 and column number 12 in the given problem, which means that at the column 12 row 12 and the column 12, I must go and I should define this value which was located as y in the given problem. So, these are the individual values which will be kept there, provided that the existing values are also added on them. So, it will not be that we will just remove the previously existing values, whatever value is already there we will add on top of it, and that is how we assemble the overall stiffness matrix of the given system. We do it in a loop where we run it for each of the member. I think we have already seen that in the previous session where we did the hands on the code. Now, based upon this idea, we generate the overall stiffness assembly, as we realize that this is a 18 cross 18 stiffness matrix of the given system. Now, this 18 cross 18 matrix has been located with respect to the degrees of freedom in the order of 1, 2, 3, 4, 5, 6 up to 7 up to 18 in the given rows, and also 1, 2, 3, 4, 5, 6 up to 18 in the given columns. So, this is in the specific order of the degrees of freedom which we have arranged in the given system. Now, as a next part of the system, we will also look to identify the joint load vector. So, in a load vector we have two cases, one which is the load directly active at the joint. So, we identify that A of j, which is the load directly active at the joint of the given system. So, to identify it, we realize that in the given problem A of j should come out of the size 18 cross 1, because there are total 6 number of joints, 3 degrees of freedom at each of the joints. So, there are total 18 possibilities of the joint forces which are possible. Out of that, we realize that only at the joint 3 there are joint forces which are active directly. So, what we get at the position of the joint 3's degrees of freedom, which are 7, 8 and 9, we put the values of these forces, and rest all the values will be 0 in the given system. So, if I keep the values at the position of the degree of freedom 1, which is 7, so it is P, at the position of 8, which is the vertical value, so it is in the negative direction, so it is minus of P, and finally along the positive z direction, this is 2P in the given system. So, I got these 3 values in the direction of x, y and z in the global directions, and these are the values in the order or in the position of the degrees of freedom 7, 8 and 9 in the given system. We can understand now that all the remaining values of the system for the given problem, they are all 0. Now, this is the joint contribution or the joint load contribution of the given system. In fact, many of the times we consider in the code at the beginning that Aj is a zeros vector, which is zeros of 18 comma 1, which means that a null vector of the 18 coefficients will be arranged, and then we only pick the values which are non-zero in the given system, because that is easier input to be provided, and then we provide that okay, Aj at the position of 7, Aj at the position of 8 and Aj at the position of 9 is being provided with these numerical values like P, minus P and 2P in the given system, whereas at the remaining places the value remains 0 only. As a next step, we go to the member load contributions. Now, when we look at the member load contributions, we see that there are 2 members which are subjected to the member loads. One is a member 1, so member 1 has a vertical load, and second is a member 4, which is also having a vertical load in the given system. Now, interestingly, in this problem we have both the loads which are active in the direction of the y. So, as this is so I'll just consider first the member of 1. So, as a simplistic case, I consider the member in this manner. This is the member which is kinematically restrained first, because as we remember, to evaluate the reactions in the given system, I think the truss problem up to now which we did was not having the member loads, but maybe the space truss as a case we have taken in which the member loads are also active. So, before going through this part, we must also accept that it is not always necessary that the trusses will not have the loads active on the member span. We can have in a real structure the loads could be active on the member span also. Only thing, while doing the analysis, we convert all these loads as the equivalent joint loads of the given problem. So, to do so, as I considered that there is a uniformly distributed load active on the given system, So, corresponding to this load, which is P upon L, I can evaluate that what is the amount of reactions which are appearing here. As it is a truss member, it will not get any amount of the reactions, moment reactions in the given system. There is no horizontal force, so there will be no active horizontal reaction component in the system. As there is no lateral force in the given system, or along say the direction of the z also there is no possibility of the force. So, both these directions will also be not getting any force in the given system. So, with this idea in mind, we can understand now that in the given system we have got the member 1, which is connected with the two of the nodes, node 1 and node 2, and at both of the nodes, if I define for the member 1 AM1 with respect to the fixed end forces, I can evaluate first the forces or the fixed end reactions in the local member coordinate, and I realize that these member coordinate values for the given system. So, as this is connected to the degrees of freedom 1 to 6, so I locate it as 1, 2, 3, 4, 5 and 6 in the given problem. So, along the degree of freedom direction 1 it is 0, along the degree of freedom direction 2 it is the WL upon 2, which means that P by 2 in the given problem, and the length of the given member is 6L for the overall system. So, this is 6P upon 2, which means it is 3P in the given vertical direction. Along the direction 3 it is 0, along the direction 4 also it is 0, this is 3P and this is 0. So, these are the loads which we have directly evaluated in fact in the global directions of the given system. One can also do it in the local directions of the system, and the local direction forces will also appear to be same, because they are just having a horizontal member in which say I can consider this to be the local x direction x of m, this could be the y of m and this could be the z of m in the given system. Once I have located these values, I can evaluate the A of member 1 with respect to the fixed end forces in the global directions, and to do so I must evaluate the R values of the given system. So, R transpose into the individual member forces which are 0, 3P, 0, 0, 3P and 0. In the same manner, if you will do this R transpose expression on the given system, you will realize that this gives you a force which is directly in the direction y. So, A of m1 with respect to the fixed end part comes out as 0, 3P, 0, 0, 3P and 0, and we understand now AE1 will be equal to minus of AM1F in the given problem. In the similar manner, now I will go with the member number 4. I realize that for member 4 also it is straight member. It will be considered first with the kinematically determinate form. So, the member is fully restrained, subjected to the load which is at the center of it. So, we will calculate the two reactions of the system which are P by 2 and P by 2 in the given system, and corresponding to it also we realize that both these reactions are in the direction of the y, no component along the x and z in the given system. So, I can directly write the AM for the member 4 with respect to the fixed end system, and this value will be 0, P by 2, 0, 0, P by 2 and 0. Right. So, these are the member forces, the fixed end forces which can be evaluated. I can now convert the equivalent joint loads for this member force also, and that comes out as the opposite of the given system. So, once we are able to do it, now I can easily identify these values. I can call that now the overall structural system will have the force which is A of G plus A of E in the given problem. A of J we have already provided because it has 18 cross 1 null vector, in which at the 3 positions at the 7, 8 and 9 I got the 3 values of the load. Whereas, when I go with the system of the member forces, I realize that AM1 and AM4 are contributing to the given system. So, we got the A of E contribution for the member 1, and the values are minus of 0, 3P, 0, 0, 3P and 0. But we also realize that these 6 values are in the position of 1, 2, 3, 4, 5 and 6 in the given system. Similarly, the AE4, which is for the member 4 in the system, is also evaluated, and those values also come out with the negative sign 0, p by 2, 0, 0, p by 2 and 0 in the given system. As these are for the member 4, we realize that the first node for the member 4, as per our idea, that for the member 4 the first node j is 4, the second node is 1. So, I will put in the same order, and with that point the first node 4, second node 1. So, it will come out with 10, 11, 12, 1, 2 and 3. So, these are the 6 degrees of freedom which are provided with respect to the member number 4, and these are with respect to the member number 1 in the given system. So, to get the overall value of the structural load system, we typically add the contributions. We write the contribution with respect to the A of j, in which only at the position of 7, 8 and 9 I am getting the non-zero values. I will just put those values in the system, p, minus p and 2p, and then I will add the A of e contribution, and we realize that A of e is identified with respect to the node 1, 2 and 3. So, this is defined with respect to the node 2, both the values are there. So, I will add it as 0, minus of 3p, minus of p by 2, 0, 0. So, this is just, we consider that this is 1, 2 and 3 position of the given system. Similarly, then 4, 5 and 6, so which are 0, minus 3p and 0. Then 7, 8, 9 are all 0. And then 10, 11 and 12, in that we got the value of 0, minus p by 2 and 0. 12. Beyond 12 up to 18, we have everything 0. Right. So, this is 13 to 18 in the given system. So, if I just add these two components, I will just add in the given system only at the position of the p, and I get this value as p minus p and 2p in the given system, and this becomes the overall load vector of the given system. So, once we have got this load vector, I can now go with the idea of the rearrangement. We have already seen that in the given system these particular nodes are fully restrained in the given problem, which means that corresponding to the node number 4, 5 and 6, we can consider that the degrees of freedom are restrained, and these are the degrees of freedom which will typically be written as 10, 11, 12, 13, 14, 15, 16, 17 and 18, whereas for the node 1 to 3, the degrees of freedom which are 1 to 9 in the given problem, they are free in the given problem. So, I can now just segregate the stiffness matrix in these two parts. It will become much more easier because somewhere the standard order of the free and the restrained degrees of freedom is very well distributed, which is 1 to 9 and 10 to 18 in the given system. So, using this system, I evaluate first the overall system, that delta f is something which I want to evaluate. So, it is unknown to me. Delta r is the restrained degrees of freedom corresponding to all these positions, and we realize that this is all restrained. So, these are all 0 values. So, there will be all 0 values corresponding to, I am just writing with respect to all the degrees of freedom. So, 10, 11, 12, 13, 14, 15, 16, 17 and 18. So, this is a null vector for the given system. A of f is the load vector corresponding to the first 9 degrees of freedom. So, we go to this point, the first, second, third, 4, 5, 6, 7, 8, 9. So, up to here we take these values from the given system, and this we define as a of f in the given problem. Right. As a next part, so I think this is what we have done. Something I think with respect to the values, just we can cross check that what has been provided here. A of f, I think one problem which we had, the value of the load which was given upward, I have taken it to be downward in the given system. So, the value of these expressions will actually be coming out to be negative. When they come out with the reactions, they will be downward in the given problem. So, accordingly this member forces will actually be coming out to be positive. I think you can see this, that the load direction is upward, which means that the reactions will be downward in the system, which are negative, and that is where the member forces will come out to be positive. Okay, I think fine. So with this idea, I think we can get the individual values of these forces, and once we generate it, the overall expression can be solved first for the unknown values of the system displacements. So I can write it as A of f is equal to S of ff into delta f. Delta r is already null vector, so I do not need to put the contribution for the second part. So I can directly write delta f is equal to S of ff inverse into A of f, and once we do it, we get the value of we get the value of the d of f, and these are all the degrees of freedom which are related to the given system. Now these are delta f for the given system. But we also realize that in the A of s, the given vector, the remaining values which are there, out of which much of it the 0 values, but at the position of 10, 11, 12, all these values which are non-zero, some of these values are the corresponding values of the AR1 in the given system, and these are the corresponding values of the reaction due to the load. So if we add these contributions in the system, we evaluate the final AR value, which is A of r from the given expression, which we evaluate as A of r equal to S of Rf into delta f in the given system. The second part, S of Rr into delta r, that is anyway 0 because delta r is null in the given system. So this A of r is obtained. After that, we are calculating the A of r final in the given problem, and that is equal to A of r minus A of r L in the given system. So the contribution due to the loading part need to be just reversed in its sign, so that it becomes the reaction of the given system. So this is the contribution of the given part. I think this we have done to get the final value of the A of r in the system. Once we are able to get the A of r in the problem, we can go to calculate the member forces. I am just doing it for the member 1. Say for the member 1, if I want to calculate the member force, the A of m1 is the fixed end force component of the system. So we will go back to the same values of the system which we have identified here. I just located the am1, which are the fixed end values of the system. So p value corresponding to the given system is defined as 240. So accordingly, this value becomes 0 minus 720, 0 0 minus 720, and that is what has been defined over here. So this is the A of member force 1 fixed ended components of the given system. This has been defined in the global coordinates. At the same time, the degrees of freedom of the system, which have been all located, these are corresponding to 1, 2, 3, 4, 5, 6, 7, 8 and 9 in the given system. I will pick out of this the degrees of freedom which are corresponding to the member 1, which are 6 in numbers. So these 6 degrees of freedom have been taken. Multiply that with respect to the member stiffness SM1. Now all of these values are taken in the global coordinates of the given system. So you multiply the SM1 with the delta corresponding to the member 1, add the contributions of the member forces, and that will give you the effective member force for the given system. So as you calculate this value, this gives you the standard expression like this. We add along with that the expressions with respect to the given system. I think yes, I think the way we have defined over here, and this value gives us the this is the member force with respect to the fixed ended part only, and these are the evaluated values. Once we convert all these values over here, we evaluate it as a global values. So these are the values which are appearing. When we convert it into the local coordinates, so these are the corresponding values for the member 1. Now member 1 in the given system, if I just look at the original problem, is over here. Now in the member coordinates, this is the direction 1, this is the direction 2, and this is the direction 3 for the given system, which are the local coordinates of the given system. Whereas in the generalized coordinate, I have the different directions of the system. So I can use the transformation rule to convert these values, and if I do the conversion to the local coordinates, I get the values as these standard values. So to convert it, I can simply use the A of m with respect to the transformed or the member local coordinate fixed end forces, r into r, which is the expression of the rotation matrix, S of mi, which is the corresponding value which we have already evaluated, delta I, which also we have already evaluated in the previous step for the given member 1, and multiplying that with respect to the rotation matrix parameters, we can get the overall value in the local coordinate as well. So, with this idea we are able to identify the overall results with respect to the general space stresses. We have implemented it into the computer based approach also, and finally these results which have been obtained, they can be further utilized to generate the member force component for all the remaining members as well. With this we stop over here. Thank you everyone.